So obviously we'll be talking about oxidations and reductions, and this may give you shivers from remembering back in general chemistry days where we learned that oxidation is loss of electrons and reduction is gain of electrons. The good news is about organic chemists, like many things from Gen Chem, we're kind of just dumber versions of a general chemist. So what we'll talk about is oxidations and reductions, and we'll kind of steer it in the direction of what we've obviously started just talking about, which is aldehydes and ketones. So one of the things that we should recognize is I kind of compare oxidations and reductions in organic chemistry kind of to the opportunity to take like a local train versus an express train. If you've ever kind of been to like a big city with a subway system, you can either take the train that kind of stops at every point along the way, or you could just take the express train, which takes you from one end to the other much more quickly. So oxidations and reductions kind of work that way in organic chemistry. So the first thing we're going to talk about is we're going to talk about primary alcohols. And honestly, these are probably, in terms of oxidations, the most interesting, I would say. So we'll just start off with a nice simple one. We'll start off with ethanol. And so obviously what we're going to be doing to this thing is we're going to be oxidizing it. It turns out the reason that we're kind of starting with oxidation here is that this carbon right here is already pretty close to as reduced as it can get in this particular series. And what we're going to do is we'll kind of just take the local train, and I'll kind of the first stop along the way here in terms of an oxidation is going to be for me to take this primary alcohol and turn it into an aldehyde. One of the things you'll notice by me taking this primary alcohol and turning that thing into an aldehyde is that I removed an equivalent of H2, right? So it turns out that anytime you do that in organic chemistry, even though technically, yes, we could go back to the general chemistry way of understanding things and we could say we are oxidizing this thing. Here, first of all, let's put oxidize, right? And this will be all kinds of different reagents that we'll talk about in just a second. So if we're going to oxidize something, we are essentially ripping electrons out of the system. And the way that we usually are going to see that in organic context is that you're going to be losing an equivalent of H2, or, as is going to be obvious in the kind of the next step of this oxidation, is we could further oxidize this aldehyde all the way to a carboxylic acid. And what you'll notice that I've added is I have truly added oxygens. And so that's how we're going to kind of understand this idea of oxidation. No longer are we going to think about it as a loss of electrons, which is technically happening, and I'll show you that in just a second, but we're going to talk about oxidation as obviously either adding oxygens or removing equivalents of H2. Right? And that's why I say that oxidations are a little bit easier to recognize in organic usually, because you really do add oxidation, or you really do add oxygens, right? That's why we called it an oxidation back in the good old days, because we thought you had to add oxygen, and later came to the understanding that we're actually removing electrons from something. So where are those electrons coming from? Well, it's all from the point of view of the carbon, right? And so it may be helpful to talk about oxidation states of carbon, which I'll put in this blue color here. So the way that you do oxidation states in the case of organic molecules is pretty similar to what you used to do in Gen Chem. So what we're essentially going to do is we're going to kind of highlight all of the atoms around this carbon, and then we're going to assign electrons depending on their electronegativities. Keep in mind, oxidation state is not a true charge for something. It's kind of a bookkeeping method that allows you to have predictive capacity. So let's highlight the hydrogens on here. And so if we look at our electronegativity guide, and we imagine that a carbon-carbon bond is kind of split evenly, right? Let's kind of do this, right? So that thing that is made up of 2 electrons, you're going to essentially put 1 electron with the carbon and 1 electron with this other carbon. It turns out that in terms of the electrons that we're going to be assigning, we're going to assign like this, right? Oxygen is more electronegative, therefore both electrons go there. That's going to tend to give a +1 oxidation state to carbon, right? But then we've got the 2 additional electrons coming from these hydrogens. So if you keep track of the kind of the 4 that it originally had, this guy is considered to have a -1 oxidation state. And we could do, of course, a similar thing to determine the oxidation state of this carbon. Keep in mind that since this is truly an oxidation going from here to here, we should see that this thing becomes some number of units more positive, right? And so there are things that that still hold from general chemistry days. It's just that this is something that we're not going to be doing that often in terms of like truly assigning oxidation states. I just wanted to show you how to do it in case you ever get a question about it. So we're going to do a similar thing here. We're going to highlight the environment around this carbon. And we'll consider the fact that that carbon normally has its 4 valence electrons. And so we're going to split those 2 evenly. We're going to assign both of these to oxygen. And then, of course, carbon's a little bit more electronegative than hydrogen. So what we end up with, if we kind of keep track of the carbon's 4 original electrons, right now it has 1, 2, 3, right? And so that means that we're going to have a +1 oxidation state here. And you'll notice that we truly have had the that -1 oxidation state did become 2 units more positive. And it kind of makes sense because we essentially ripped out an equivalent of H2 with its 2 electrons right here, right? And so we could do the same thing over here. And of course, it's already expanded. Whoops, I screwed that up already. All right, in this case, we're going to assign pretty much all the electrons but 1 to the oxygens here. So we end up with a +3 oxidation state. Okay, so we're not going to talk too much more about oxidation states. If you have questions about how to assign those, feel free to ask. But what we are going to talk about are different reagents that allow us to either do the express trip all the way over to here. And then once we have a pretty good understanding of the express trip type reagents, then we'll start to develop this idea of kind of taking the local train, right? What kind of reagent might I be able to use in order to only partially oxidize my carbon, right? And then there are also sets of reagents that'll take this thing and oxidize. Quite honestly, usually when you do these types of oxidations, if there's nothing else in the molecule, you just, it wouldn't really matter what you used. You just use maybe the express train all the way. The times where you want to be a little bit more judicious about what reagent you choose is, let's say you had an aldehyde that you wanted to oxidize, but you didn't maybe want to oxidize an alcohol as well, right? And so all of these in oxidations and reductions are going to be kind of a glorified note card reaction kind of day. So let's get right into it. Okay, so I just redrew everything here and recognize the fact in primary alcohols, we're going to go from the primary alcohol. We could go to the aldehyde, and if we used a strong enough reagent, we'd go all the way to the carboxylic acid, right? And so this is kind of a spectrum. Keep in mind that we're going in the oxidation direction right now. So this direction is oxidation, and obviously if we wanted to go back, these would all be reductions, and there are some reagents that would allow us to do that. But I will say that it's a little bit like the reductions are a little bit harder, right? It's almost as if like it's an all or nothing kind of thing. It's a little bit harder to kind of do this little hopscotch of local trains here. Usually you just have like a reagent that'll just go that direction. So if you actually have to stop at the aldehyde, you have to kind of do this, crazy thing where you reduce this thing all the way and then oxidize it to here. Oxidation's a little bit easier to control. So let's take a look at some of those reagents. So first, the express train, right? Well, what kind of reagents can take us all the way from here all the way to here? Well, it turns out the most major ones are things like potassium permanganate. KMnO4 is a really great express train. There's other named reagents that are all involved this different types of chromium species. So a really typical looking one might look like this, right? Sodium dichromate. Sometimes these things are written slightly differently. You can actually show it as the acidic version. Dichromic acid. There's other instances where you might see something written as, let's say, CrO3 and with some sort of acid, right? These things, all these things are pretty much equivalent. What you're looking for is some sort of, just kind of normal chromium-6 type species. And oftentimes, anytime you've got this species with a little bit of acid, this is something that you might just see abbreviated as Jones reagent. The important thing to recognize is with these type of oxidants, first of all, you might recognize them as the oxidants because you have a whole bunch of oxygens present, right? And so that's going to pretty much push you all the way to the carboxylic acid. And by the way, if you were an aldehyde and you happen to see any of these, you absolutely would get pushed all the way to kind of the end of the line, right? So far more interesting. So let's call these the express train or express reagents that brings us all the way to the end of the series. Much more interesting, though, are the different note card type reagents that just do this step. It turns out, as we'll see when we start to talk about aldehydes are incredibly synthetically useful. Carboxylic acids, somewhat less so. And so there are many, many, many named reactions that are going to take us from a primary alcohol and stop at the aldehyde. So I'm just going to go ahead and list out a couple, and I'll just mention a couple of interesting things. Okay, so the local train we're taking right now is going to take a primary alcohol, turn it into an aldehyde. The ones that I would recommend knowing to put on a note card are these various names here. So one is the Swern oxidation or Svern oxidation. Just in case you have to recognize it without the name, that involves DMSO, COCl2, and that should be triethylamine. And this, by the way, is called oxalyl chloride. We also have probably the most popular one on the ACS, which is oxidation with Pyridinium Chlorochromate, or PCC. Usually you can recognize that from the presence of pyridine HCl in anhydrous conditions with CrO3. And then also this crazy Des-Martin reagent, which I think is called the pyridoxide or pyriodane or something like that. But it's this crazy looking iodine species with a whole bunch of acetate groups. You can't miss it. So these are all pretty important reactions. There's tons of them that will kind of do this one little local train. I will say there is a local train reagent that is only able to take aldehydes and to turn them into carboxylic acids that won't touch the primary alcohol, and it's helpful in a lot of synthetic protocols, so I'll just give it to you here. So we'll call it local to carboxylic, and that involves silver plus. And any kind of salt of silver will do this kind of aldehyde to carboxylic. So hopefully that'll kind of help you to organize some of these. Any of these mechanisms that you'd like to look up in the book, your book does a pretty good job of highlighting at least some of them. So the one thing that is common to all of these express reagents here that is not true of all of these is the presence of water, right? And so when we start to get into hydrations and things like that, you'll kind of see why water is such an important step in terms of going all the way to the carboxylic acid. So one thing hopefully you'll notice about the oxidation of secondary alcohols is it's pretty friggin' boring, right? There's no need for talking about local trains, express trains, or anything else. It turns out that a secondary alcohol will always go to a ketone, and that set of oxidations right there pretty much includes everything that we just talked about, right? Any single one of those is going to be a powerful enough oxidizing agent to go all the way to the ketone. And of course, I should mention there are some reagents that, well, there's one I can think of that if it's synthetically useful to you, I think it involves tempo and bleach essentially is one set of reagents that will just touch a secondary alcohol and turn it into a ketone, but will leave a primary alcohol alone. I think there's one question somewhere on a homework that I put out that involves that. So I'll just write that down. Tempo, by the way, is just a unusual looking nitrogen species that looks something like that, right? Where there's this kind of oddball oxygen connected to a nitrogen, and then also bleach, right? And so that's the only reason that I mention that is it might help you out as a note card reaction somewhere. Let's take a look at tertiary alcohols. Well, pretty boring one. Tertiary alcohols, right? You can try to oxidize them. The only thing you're going to do is destroy the compound, or there's going to be absolutely no reaction. So don't have to worry too much about that. So now let's flip it a little bit and let's talk about some reducing agents. And as I said, those things are kind of an all or nothing kind of thing. Okay, so I've arranged this presentation just a little bit differently. What I've done is I've put the hardest reduction to do at the top, right? The one that takes us all the way from one end to the other. And then I have these kind of little mini, little bit easier to achieve reductions down towards the bottom here. Keep in mind that if an oxidation was adding oxygen or removing an equivalent of H2, reductions are the exact opposite of that, right? We're going to be adding equivalents of H2 and or removing oxygens, right? So what is true is that the things that can take this carboxylic acid all the way to the primary alcohol are also going to be plenty enough to do these other two reductions. And probably the most common one is something called lithium aluminum hydride. That's kind of the big gun. And one of the things that you're going to notice about any time we use lithium aluminum hydride, or really anytime we use a hydride to reduce, is we're always going to need a second step in order to quench the O- species that we would otherwise end up with. So lithium aluminum hydride, right, that's going to be able to do any of these reactions right here. The slightly, I guess, weaker or kind of not as intense one, which I guess I'll just put over here, is going to be something called sodium borohydride. So just in terms of getting note cards that kind of allow us to do some synthetically useful things in the very near future, these are the two reagents that we're going to start off with reductions. We're not going to talk about this as much as we talked about oxidations. We'll kind of pick up more kind of more interesting reducing reagents as we get a couple of more interesting functional groups. But for this chapter, these guys will get us done, right? So a sodium borohydride with an H3O plus quench is going to be an excellent choice for aldehydes to primary alcohols, and also for ketones to secondary alcohols. The thing that is not going to happen with a normal sodium borohydride is that it's not going to be able to do much of anything in terms of reducing a carboxylic acid all the way to a primary alcohol. So hopefully these have been some pretty useful note card reactions, definitely things that we're going to start to see more and more in synthesis.